In this video, we'll be graphing rational functions. Let's go over our steps for graphing a rational function. So let f be a rational function given by f of x equals n of x over d of x. The first thing we want to do is simplify the rational function and identify any holes. Recall that we simplify our rational function by factoring the numerator and denominator and looking for a common factor. After we've simplified and identified any holes, we want to find the asymptotes. Be sure to use the simplified version of the rational function anytime you're finding asymptotes. Next, we want to find the x and y intercepts of the function. Again, be sure to use the simplified version of the rational function when identifying intercepts. Fourth, we're going to draw the intercepts and asymptotes on our graph. Fifth, we're going to find additional points on the graph, particularly near the asymptotes. The way that we're going to get these additional points is simply by creating an XY chart, choosing X values around our vertical asymptotes, and then finding corresponding Y values. Be sure when finding these additional points that you use the original rational function, not the simplified version. We'll plot those additional points and then draw in a smooth curve to complete the graphs between and beyond the vertical asymptotes. So here goes. Let's graph the function g of x equals 2x squared minus 7x plus 6 over x squared minus 3x minus 4. We want to identify any holes, asymptotes, x-intercepts, and y-intercept. We always want to start by seeing if the function can be simplified. So we'll start by factoring g of x. Our numerator factors into 2x minus 3 times x minus 2, and the denominator factors into x minus 4 times x plus 1. Notice there are no common factors. That tells us that there are no holes in the graph of this function. Next, we look for vertical asymptotes. Vertical asymptotes occur at the zeros of the simplified denominator. Our denominator didn't simplify, so we're just looking at the original denominator. We have factors of x minus 4 and x plus 1. Each of those factors is going to give us a 0. We're going to have two vertical asymptotes at x equals 4 and x equals negative 1. Remember that you need to write the x equals for each one of the vertical asymptotes. We are writing equations of lines. Next, we're looking for horizontal asymptotes. This is where we compare the degree of the numerator with the degree of the denominator. Well, if we look at our original, I think it's easier to look at a multiplied out version. And since this didn't simplify, we can just turn our attention to the original. Here, the degree of the numerator is equal to the degree of the denominator. When that happens, we have a horizontal asymptote at the ratio of the leading coefficients. We got a little invisible 1 here. So the ratio of our leading coefficients is 2 over 1, or just 2. So that's a horizontal asymptote at y equals 2. Oblique asymptotes exist only when the degree of the numerator is exactly one larger than the degree of the denominator. Is the degree of the numerator one larger than the degree of the denominator? No, it's not. Therefore, we have no oblique asymptote. Next, we want to check for intercepts. To find the x-intercept of anything ever, we let y be equal to 0 and solve for x. I have 0 equal to our original function. Recall that I can put this 0 over 1. I now have a proportion, and we can cross multiply to solve. 0 times the denominator gives us 0, and 1 times the numerator gives us the numerator. We get the equation 0 equals 2x squared minus 7x plus 6. And we solve this equation. I'm going to solve by factoring, but notice we already factored that polynomial over here. Rather than redoing the work, I would just look to what I had already done. We get 0 equals 2x minus 3 times x minus 2. We set each of our factors equal to 0 and solve. 2x is going to be 3, making x 3/2, and x equals 2. We have two x-intercepts, and since they're x-intercepts, I need to be sure to write them as ordered pairs with a y-coordinate of 0. Next, we find our y-intercept. To find the y-intercept of anything ever, we let x be equal to 0 and solve for y. So that's going to be 2 times 0 squared minus 7 times 0 plus 6 over 0 squared minus 3 times 0 minus 4. We've got a lot of multiplication by 0 here. All those terms are going to fall out, leaving us with 6 over negative 4, which is negative 3/2. Our y-intercept is the ordered pair 0, negative 3/2. At this point, we want to plot all of the information that we have. So we have two vertical asymptotes, one at x equals negative 1, another at x equals 4, and then we have a y-intercept at y equals 2. Fortunately, my highlighter won't go skinny this way. I'm going to plot the 3 points that I have. 0, negative 3/2, 3/2, 0, and 2, 0. Now you'll notice that I drew the asymptotes in a different color from the points. The asymptotes aren't actually part of the graph. The asymptotes are a guideline for the graph, not actually part of the graph. So I have these 3 points, and I know they must connect, but other than that, I don't know much about this graph. We're going to obtain some additional points so that we have more information about the graph, and can draw in our curves. We're going to make an XY chart to get additional points. We want to choose numbers. Notice how the two vertical asymptotes break up our plane into three regions. We have, all this over here to the left of the leftmost vertical asymptote. Then we have the region in between the two, and then we have the area to the right of the right one. We want to choose X values in each of these three regions. So I'm going to choose X values of -7, -2, 3, 5, and 8. To get the corresponding Y values, we plug these X values into our original function. For the sake of time, I've already done that. With X equals -7, we get 2.3. With -2, it's going to be 4.7. +3, we're going to have 0.8. +5, we're going to get 3.5. And 8, we get 2.2. Now let's graph these 5 points and then see if we have enough information that we can draw in our graph. First up is -7, 2.3. Right here. And -2, 4.7. I know that these 2 points have to connect. And I also know that the ends of my graph have to tend towards the asymptote. So to the left, we're just going to get closer and closer to our horizontal asymptote. And to the right, we're going to get closer and closer to this vertical asymptote. Now here in the middle, I just chose 1 point, 3. It's the -0.8. When I plot that, I know that these points have to connect. I also know that the ends of the graph have to tend towards an asymptote. So here on the left, we're going to tend towards that vertical asymptote, and on the right, we're tending towards this vertical asymptote. Our next 2 points, it's going to be 5, 3.5. And 8, 2.2. These points must connect, and the ends of our graph have to tend towards the asymptotes. So the left end of this portion will tend towards our vertical asymptote, and the right end of this portion of the graph will tend towards our horizontal asymptote. So there we have the graph of g of x equals 2x squared minus 7x plus 6 over x squared minus 3x minus 4.